Good morning, ladies. Good to have everybody here today, except for Emily. I hope she's watching. I think she is. So we're to example 12. Yesterday did we introduce Betsy Botu yesterday? Okay. So this one here, we're going to have horizontal asymptote for number 12. What's going to be our horizontal asymptote here? Y equals
zero.
Y equals 0. So why is Y equals 0 our correct answer?
How did you see that? I can't see all those numbers. It looks like a 2.
This looks like a 2 here?
The bottom one, yeah. I thought they were the same.
Oh, you did? Okay, yeah. Yeah, sometimes the resolution isn't really good. But do you see why this is a horizontal asymptote of Y equals 0?
Yeah, once I seen that it was a 3.
Yeah, so once you read this, so Emma's having trouble reading.
Go bigger on bottom.
Bigger on bottom.
0.
Yeah, so as we go toward infinity, this thing is eventually going to approach 0, is what it amounts to. Okay, this example 13, do we have a horizontal asymptote here for 13?
4 and 5. Yep.
So we have a horizontal asymptote of
4/5.
Y equals 4/5. Okay, how'd you get that?
It's the coefficient. Betsy.
The coefficients, right? Now, for number 14, we have limit at 3x cubed minus 23 over 4x minus 1. So our horizontal asymptote is what?
Does not exist.
Horizontal asymptote does not exist. So you almost said that. I heard about 3 of you say that, like in stereophonic delivery. That was pretty good.
Yeah, pretty good.
So you see that, and if you look at it, it looks like we're going to be approaching infinity. That's what it looks like, both each way, I think. Okay. So is everybody pretty clear on that? Is that pretty easy? Now on the AP calculus test, these problems will come up occasionally. When they come up, they're going to be in context of sort of a more difficult thing. Remember the last one we did yesterday, where we had to figure out like A plus C? That was a more difficult problem. But you'll see problems like this that are that straightforward, that easy. Okay. Now this 15 looks like as x approaches negative infinity, doesn't it? That's what it looks like. So what is this going to be here as x approaches negative infinity? Does not exist? Let's see this, because what happens is this is a weird kind of thing, isn't it? Divided by that. And I'm thinking this is a does not exist one, because if you're dividing by the fraction, it's the same as what? Dividing by the fraction is the same as multiplying by the reciprocal, right? So if we go ahead and just change that and multiply by x over 1, that's going to multiply by x. And once we do that, what is that going to be? Bigger on top. So that's going to be a does not exist. So this is kind of a weird one right here. So let's go ahead and look at 16. What is 16 going to be? 1/2. 1/2?
Y equals 1/2.
Y equals 1/2, okay? So I think it is y equals 1/2. How did you get that? How did you get y equals 1/2?
Well, the square root of that is, the square root of squares is just going to cancel out. So then it's just the coefficient of the coefficient, and it's 1/2.
Yeah, so you have to, that's pretty challenging, because you have to kind of ignore this, don't you?
Oh wait, but there's a...
You kind of ignore it.
Yeah.
And so we're going to be approaching 1/2 as we go to the right. And one thing when you have a calculator, a calculator is very helpful to check these things. So it's the kind of thing you're expected to do these things without your calculator, but so we have x squared, and we have x squared, I want to get this right,
Minus 3x.
minus 3x over 2x plus 1. Over 2x plus 1.
Yes.
And when we graph this initially, we really can't see, I mean, it looks like it could be approaching 1/2, but what you're going to do, if you go here to table set, and you set this to ask, you'll be able to put in a real big number and see what that is, right? So you go over here, I'm going to put in 1 million. And we'll see if Hannah was right. Was Hannah right, or was she right? She was right. So that was good work. That's some good work. But really, when you use a calculator in this class, most of the time that's the way I want you to use it, where you kind of go to corroborate. Okay, this one over here, it's the same one, isn't it? Example 17, no, it's to negative infinity.
Yeah.
So what is this one going to be here?
1/2, y equals 1/2.
Okay, it should be y equals negative 1/2. And again, we could check in our calculator. I'm going to go here.
Yeah, if she put negative, she just makes it in with the equal sign.
Yeah. There we go. Yeah. Okay. Negative 1/2. Okay, some good little problems there. Okay, now we come to Notecard 5. And Notecard 5 is sort of an alarm for me, because I know that the packets you have so far only go through Notecard 5. So what does it tell me I need to do this afternoon?
Print out some more.
Get some more packets going for you. So it gives you something to look forward to. I know Kaylee's binder, those papers are getting a little bit lonely in there. They need some company.
We got plenty of friends. There's 30 pages right now.
Yeah, okay, good. So anyway, what we have is, do you remember that day last week when we only had like 4 people in the classroom? Remember that?
Yeah.
I think it was the volleyball tournament, wasn't it?
Yeah.
And so what happened is that we had a short class, plus we watched a video, didn't we?
Yeah.
And the video, remember the lady in the video talked about this thing right here? Remember that? And so what happens is, now we're getting to the logic part of calculus, that a function is continuous if condition 1, condition 2, condition 3. So when you're asked to justify continuity, what I expect you to do is write down these things. And you get to step 1. If step 1 doesn't apply, let's say f of c is not defined, well then you've proven discontinuity. If it is defined, you go on to step 2. Then you check the limit. The limit exists. F of c is defined, the limit as x approaches c exists. So these two exist. And then 3, here, the last step, this has to equal this. So the actual value of the function has to equal the limit. If they both exist and are the same thing, then you've proven continuity. And so you just write it out like this. Therefore, okay, these conditions are met. Therefore, well, we're going to work these out. And then we also have the properties of continuity, and you have product, quotient, and then you have a composition of functions too. That's what this one is. That's a composition of functions. So what it means is that if two functions are continuous, or if a function is continuous, you can multiply that by a scalar by a number, and that will still be a continuous function. If two functions are continuous, the sum or the difference of those functions is also going to be a continuous function. You can have the product of two functions that each one of which is continuous, you're going to have a continuous function. Now for a quotient, that's a little tricky because you're going to have continuity except where the denominator is equal to 0. So that's all this is saying. And then the composition of functions. So those things are just properties, continuity. And so now we come to some examples of that. And I'm going to work one of these out and show you. And so this is one where we have a critical number. What is a critical number here? Well, it's this one right here, because this is what kind of functions we call this? A piecewise function. Excellent. Excellent work. Okay, so I owe Kaylee, and I owe Hannah, and I owe Emma so far today. Thank you, ladies. All right. So what happens is we're going to test at 3. So condition 1, f, it's actually h, right? So h of, we're going to check. Now do you realize that this function is going to be continuous everywhere else besides that? We have polynomial function here, polynomial here, polynomial here. So all these on their own will be continuous everywhere, but h of 3, I mean h of negative 2, because that's the thing we're looking at, right? H of negative 2 is what? What's h of negative 2? It is 3, right? H of negative 2 exists, because that's condition 1, right? Exists and is equal to 3. Okay, we know that. Okay, next condition is limit exists, right? So limit of as x approaches negative 2, does that exist or not? Do you know that yet? I don't know it yet because we haven't tested it. So what do we have to do to test to see if that limit exists?
Then look out. Plug it in.
It's non-calculator. So what it is, it exists, limit exists if and only if the limit as x approaches negative 2 from the left of h of x equals what? Equals limit as x approaches
2 from the right.
negative 2 from the right of h of x. So what I'm going to do for that is I'm going to put sometimes I like to put a question mark on top because we don't know it until we figure it out, right? So let's plug in negative 2. So here's, which one is our left one?
The negative one?
Okay, the left one is this one, right? Because we're to the left. So what I'm going to do is I'm just going to plug in, I plug in for negative 2 times negative 2 plus 3, and that's going to be equal to negative 2 here, cubed, minus 6 times negative 2 plus 3. And we're going to test to see if they're equal, right?
Yeah.
So on the left side we have 4 plus 3, 7. And the right side we have, that's negative 8 plus, isn't that negative 8?
Yes.
Plus 12. What's negative 8 plus 12? 4 plus 3. So that's 7. So yes, so limit as x approaches negative 2 equals 7. So the limit exists. So exists and is equal to 7. So now condition 3, the limit, so f of, or h of negative 2 equals limit as x approaches negative 2 of h of x. Are those equal to each other?
No.
No, they are not. Okay, so what you do is you press this, you say, then you conclude, therefore, h of x is not continuous at x equals negative 2. Okay? So this is a logical process of going through those steps. Now, if you graph these two functions next to each other, what would you see at negative, if at and around negative 2? What would that look like? Because we get down to graphically. So we graph these two functions. Here at x equals negative 2, what are we going to see? Well, we know we're going to see h of negative 2 is 3, right? We're going to see that right here. But what else are we going to see? We're going to see this function right here, coming right here. Boom, right? And what are we going to see over here? I don't know exactly what it looks like, but you know what it's going to do, right? The thing is just going to approach right here somehow. I don't know what it looks like. But you know that's what it's going to look like, right?
It'll be a hole.
It'll be a hole, right? There's a hole, considering these two pieces, you have a hole, but then the value of the function itself at negative 2 is going to be down below, because the hole is going to exist at the output value 7. Does that make sense?
Yeah.
Okay. And I'm going to ask you a lot, does this make sense? Because one thing that impresses me as I go through this is that, have you noticed, like I do, that in these problems there's just a lot of moving parts to them you got to keep track of, and so that's a challenge. But there's a way to do it to stay organized, and that's what we're going over. Okay, next we look at it, and usually these problems will be less tedious than that, will be easier to get to. So now we have an actual AP question here. If the function f is continuous and if f of x equals this, when x does not equal 2, what is f of negative 2? Okay, what this is, if we factor this out, what are we going to get? X plus 2, x minus 2, right? And it's going to be over x plus 2. So what's going to happen? So what we're going to do is the thing is going to look like x. It'll look like x minus 2 like this. And what happens here at negative 2? So what is f of negative 2 going to be? To make this continuous, what has to be filled in here? Right here, right? So what is that going to be? What do you have to plug in? Yeah, plug in -2. So if you plug in -2, so what is going to be f of -2? I get -4, right? Because we have x minus, you have -2 minus 2. So -4 is it. So this is one where we actually have to figure what that point is to plug it in. So -4 is it. Let's go here. See. Okay, for what values of the constant c is the function g continuous over all the reals? How do you determine continuity? The three things are what? Exist is defined or exist, right? Limit exists, and they are the same. Well, in this case, what we're given is one thing you're always looking for when you have a piecewise function. You got to have a greater than or equal to or less than or equal to. If you ever see one of these things here and there's no little line underneath, you know the function isn't continuous because the thing doesn't exist. And so what you're going to do is, you know the thing's going to exist because this is the left side, so you got to find where the limit is. So you got to deal with condition 2. So we put the limit as x approaches 3 from the left side of g of x equals limit as x approaches g from the right side of g of x. And so what do you put in here for this? What's the left side one? Okay, it's going to be cx plus 1, right? Equals, and I'm going to put question mark. That's not going to be question mark because you're going to figure out what it's going to have to be, excuse me. Then you put c x squared minus 1. So what do you do next? What do you plug in for x? Plug in 3. So we have on the left 3c plus 1 equals, that's going to be 3 squared, 9c minus 1. So what do you get for this?
30C, minus 6C.
So if we add 1 here, subtract 3c here, subtract 3c here, we get 2, that's plus 1, right? 2 equals 6c, right?
C equals 3.
So I get c is equal to 1/3 is what I'm getting, right?
That's
C is equal to 1/3. But anyway, this is a good example of the type of problem we have. So if C equals 1/3, we can test to go back. So anyway, we're working on these types of problems. We're going to apply that. So we're going to do more of that tomorrow. And that's going to be our class for today. Thank you, ladies.